Welcome to Sleepless Philosophers, where deep ideas meet restful nights. If you enjoy these journeys through philosophy, please like and subscribe and turn on notifications for daily uploads. To support the channel, consider leaving a super thanks. Any amount helps us continue creating content. You can also become a member to request video topics. We're not monetized, so your support truly makes the difference. Now let the philosophy begin. Richard's paradox. In 1905, the French mathematician Jules Richard discovered a paradox that strikes at the heart of how language and mathematics interact, revealing that certain kinds of definitions can generate contradictions no matter how carefully they're constructed. Consider the set of all real numbers that can be defined in a finite number of words using the English language. And this set seems reasonable at first because most numbers we ever think about can be described in some way. Pi is the ratio of a circle's circumference to its diameter. The square root of 2 is the length of the diagonal of a unit square, and so on. Since there are only finitely many words in the English language and only finitely many ways to arrange them into sentences of any given length, there can only be countably many such descriptions, which means there are only countably many real numbers that can be defined in this way. Yet the real numbers are uncountable, as Georg Cantor proved, which means there must exist real numbers that cannot be defined in any finite number of English words, numbers that are forever beyond the reach of language, numbers that exist but cannot be named or described or pointed to in any way. Now comes the paradox. Consider the real number defined as follows. Let it be the first real number in the set of all real numbers that cannot be defined in a finite number of English words, arranged in some standard ordering, such as numerical order. This definition appears to successfully define a specific real number, and the definition itself uses only a finite number of English words, which means the number it defines belongs to the set of numbers that can be defined in a finite number of words, but the definition explicitly states that the number belongs to the set of numbers that cannot be defined in a finite number of words, and so the contradiction emerges, sharp and unavoidable. If the number can be defined, then it does not belong to the set of undefinable numbers, but the definition picks it out precisely as a member of that set. And if it cannot be defined, then the definition fails to refer to anything at all. And yet the definition seems perfectly coherent, grammatically correct, and mathematically precise. Richard's paradox exposes a fundamental problem with the concept of definability, the idea that we can cleanly separate describable objects from indescribable ones, because the act of describing the indescribable creates a loop that collapses into contradiction. Some logicians argue that the phrase cannot be defined in a finite number of words is itself vague or improperly formalized, that it mixes informal natural language with formal mathematical concepts in a way that generates confusion, and that a more rigorous treatment would prevent the paradox from arising. Others suggest that the paradox reveals a hierarchy in language, that definitions must be made within specific formal systems, and that talking about all possible definitions requires stepping outside the system into a meta-language, and that mixing these levels is where the contradiction appears. Alfred Tarski developed this idea into a full theory of truth and definability, showing that no language can fully express its own semantic concepts without risking paradox, that truth and definability must always be relativized to a particular formal system, and that higher order languages are needed to talk about lower order ones. Richard's paradox also influenced the development of computability theory, because the question of whether a number can be defined in a finite number of words is closely related to whether it can be computed by a finite algorithm, and paradoxes like Richard's helped clarify the distinction between computable and non-computable reals. The paradox remains a haunting reminder that language, even mathematical language, has limits, that not everything that exists can be captured in words, and that the boundary between the describable and the indescribable is not as stable as it first appears. The bald man paradox. A man stands before a mirror, his hair full and thick, and no one would call him bald, this much is certain. And yet time passes, and hairs fall, one by one, slowly at first and then with gathering speed. And the question that haunts philosophers is simple and unanswerable. At what precise moment does this man become bald, after which single hair crosses the threshold from not bald to bald? And the intuition rebels against the idea that one hair could make such a difference, that the removal of a single strand could transform a person's category, could change a truth about them in such a fundamental way. The bald man paradox is a version of the Sorites paradox, focused specifically on baldness, but illustrating the same underlying problem about vagueness, boundaries, and the limits of classification. And it asks us to consider whether baldness admits of sharp boundaries, or whether it is inherently vague, a matter of degree rather than kind. And if it is vague, then how can we use the term meaningfully? How can we say that someone is bald or not bald when there seems to be no clear line separating the two states? Imagine the process in reverse, starting with a completely bald man, hairless and smooth, and now a single hair appears on his head, and surely one hair does not make him not bald. The presence of a single hair is negligible, imperceptible to casual observation, and if one hair does not change baldness, then neither does two, and if two do not, then neither does three. And this reasoning continues, step by step, until the man has a full head of hair, and yet according to the logic he should still be bald because no single hair made the difference. And this conclusion is absurd, and so something must be wrong with the reasoning. But what? The paradox forces a choice between several uncomfortable positions. One option is to accept that there is a sharp boundary, a precise number of hairs that separates bald from not bald, perhaps 10,000 hairs or 5,000 or some other specific number. And anyone with fewer hairs than this threshold is bald, while anyone with more is not bald. And this view preserves classical logic, maintains that every statement is either true or false, that vagueness is merely epistemic, a matter of our ignorance about where the true boundary lies. But this position strikes many as implausible because it seems arbitrary. There is no principled reason why 10,000 hairs should be the cutoff rather than 10,001, and the idea that baldness depends on such a precise count feels wrong, disconnected from how we actually use the term. Another option is to reject the idea of sharp boundaries and embrace the view that baldness is genuinely vague, that there are borderline cases where it is neither determinately true nor determinately false that someone is bald, cases where the world itself does not settle the question. And this view requires abandoning or modifying classical logic, accepting that by valence, the principle that every proposition is either true or false does not hold for vague predicates, and this leads to various non-classical logical systems, three-valued logics where propositions can be true, false, or indeterminate, fuzzy logics where truth comes in degrees ranging continuously from 0 to 1, supervaluationism where a statement is true if it is true on all acceptable ways of making the vague term precise, and each of these approaches has costs and benefits. Each preserves some intuitions while sacrificing others. A third option is contextualism, the view that whether someone is bald depends on the context of utterance, on the standards and purposes operative in a given conversation or situation. And in one context, a man with 5,000 hairs might count as bald, while in another context only someone with fewer than 1,000 hairs would count. And this view makes baldness relative rather than absolute. And it explains why borderline cases feel uncertain, because in borderline cases the context has not provided enough information to determine which standards apply, but contextualism faces challenges too. It must explain how context determines standards, whether there are constraints on what standards can be operative, and whether contextualism avoids the Sorites paradox or merely relocates it to the question of when contexts shift. The Bald-Man paradox also connects to broader questions about language, reference, and the relationship between words and the world. Because if most predicates in natural language are vague, and they are, nearly every adjective and many nouns admit of borderline cases, then vagueness is not a peripheral issue, but a central feature of how we communicate, and any theory of meaning must account for it, must explain how. Vague terms can be useful and informative despite their lack of sharp boundaries, and must address whether vagueness is a feature of language, of thought, of the world, or of all three. Some philosophers argue that vagueness is purely linguistic, that the world itself is precise and determinate, but our words are blunt instruments that fail to carve reality at its joints, while others suggest that vagueness exists in thought as well, that our concepts are themselves fuzzy, and still others propose that the world itself contains vague objects and properties, that reality does not always come with sharp boundaries, that nature is continuous and gradual in ways that resist precise classification. The paradox has practical implications as well. In law, where terms like reasonable and substantial and significant must be applied to real cases despite their vagueness. In medicine, where diagnostic criteria often involve thresholds that are somewhat arbitrary. In ethics, where drawing lines between permissible and impermissible actions may require confronting borderline cases where intuition provides no clear guidance. And in each of these domains, the Bald-Man paradox is not merely an abstract puzzle, but a genuine obstacle to clear thinking and fair judgment. The paradox also raises questions about personal identity and change over time. Because if baldness is gradual, then so are many other properties, aging, growing, learning, and if there are no sharp transitions, then perhaps personal change is also vague. Perhaps there are cases where it is indeterminate whether someone is the same person they were years ago, whether they have changed in significant ways or remained essentially the same. And this connects to deeper issues about persistence, continuity, and what it means to endure through time. The bald man stands as a symbol of all borderline cases, all situations where reality resists the either-or structure of classical logic, where predicates fade gradually from clear application to clear non-application, passing through a twilight zone where truth becomes uncertain, and the paradox endures because it exposes a tension between the precision we expect from rational thought and the vagueness inherent in the world and in language, and no solution has won universal acceptance. Philosophers continue to debate whether to accept sharp boundaries, revise logic, relativize truth to context, or adopt some more radical approach. And the bald man remains poised between categories. Neither clearly bald nor clearly not bald in the borderline cases, a living embodiment of the limits of definition, a reminder that the world does not always cooperate with our desire for clarity, and that some questions may have no determinate answer, not because we lack knowledge, but because the questions themselves presuppose a precision that reality does not provide. And the hairs fall one by one, and baldness approaches, and no single hair marks the moment of transformation, and the paradox persists, unresolved and perhaps unresolvable, a permanent feature of the conceptual landscape we must navigate, a crack in the foundations of logic that cannot be sealed. The arrow paradox. Motion seems so simple, so obvious. An arrow flies through the air from bow to target, and no one doubts that it moves. Yet the ancient Greek philosopher Zeno of Elea posed a question that has troubled thinkers for over 2,000 years, a question about whether motion is even possible at all. And this is the arrow paradox, one of Zeno's many arguments against the reality of change and multiplicity. Consider an arrow in flight, frozen at a single instant of time. At that precise moment, the arrow occupies a specific region of space exactly equal to its own length and width. It is not in two places at once. It is simply where it is motionless, static, indistinguishable from an arrow at rest. At the next instant, the same is true. The arrow occupies a space equal to itself, motionless at that frozen moment, and at the next instant, and the next. And if time is composed of a sequence of such instants, then at every instant the arrow is motionless. And if the arrow is motionless at every instant, then how can it be said to move at all? For motion would require the arrow to be in more than one place at a single instant, or to be in a state of transition rather than a state of rest, and yet at any given instant there is no motion, only position. Zeno used this paradox to support the Eleatic philosophy of Parmenides, which held that change and motion are illusions, that reality is a single, unchanging whole, and that the apparent diversity and movement we perceive are mere deceptions of the senses. The arrow paradox strikes at the very concept of instantaneous velocity, the idea that an object has a speed at a single moment in time, and Aristotle attempted to refute Zeno by arguing that time is not composed of indivisible instants, but is continuous, that motion is not a series of static positions, but a process that unfolds over intervals, and that the paradox arises only if we mistakenly treat time as a collection of frozen moments, rather than a flowing continuum. Modern physics offers a different resolution through calculus, where velocity is defined as the derivative of position with respect to time, a limit that describes how position changes as the time interval approaches zero. And in this framework, instantaneous velocity is a well-defined concept. The arrow does have a speed at each moment, even though speed is not a property that can be observed in a single instant, but only inferred from the relationship between position and time. Yet some philosophers argue that the arrow paradox still points to something genuine and unresolved, a mystery about how the static and the dynamic relate, how a series of stillnesses can add up to motion, how being in a place can somehow become moving between places. Quantum mechanics adds another layer to the puzzle, because at the subatomic level, particles do not have definite positions and velocities simultaneously. The Heisenberg uncertainty principle states that the more precisely we know a particle's position, the less precisely we can know its momentum. And in some sense, the arrow paradox prefigures this strange quantum behavior, the idea that motion and position are not entirely compatible descriptions of reality. The paradox also connects to debates about the nature of time itself, whether time is discrete or continuous, whether it flows or is an illusion, whether the present moment is all that exists or whether past and future are equally real, and whether change is fundamental or derivative. Zeno's arrow hangs suspended in thought, motionless at every instant, yet undeniably in flight, a puzzle that refuses to vanish despite millennia of analysis, a reminder that even the most basic experiences, the flight of an arrow, the passing of time, the reality of motion, rest on assumptions that can be questioned, that beneath the surface of the obvious lies a tangle of conceptual difficulties that no amount of mathematics or physics has entirely smoothed away, and the arrow flies still, or perhaps it never moved at all, frozen forever in the paradox that bears its name. The Achilles and the tortoise. Achilles, the swift-footed hero of Greek legend, agrees to race a tortoise, and to make the contest fair, the tortoise is given a head start, perhaps 100 meters, and the race begins, and Achilles runs swiftly toward the point where the tortoise started. But by the time he reaches that point, the tortoise has moved forward a small distance, perhaps 10 meters, and so Achilles runs toward that new position. But again, by the time he arrives, the tortoise has advanced a bit further, perhaps 1 meter, and this process continues. Each time Achilles reaches where the tortoise was, the tortoise has moved ahead. And it seems that Achilles can never quite catch up, never quite overtake the slower creature. And yet common sense insists that, of course, Achilles will pass the tortoise. That speed wins races, that the faster runner always overtakes the slower, given enough time and distance. And this contradiction between logic and intuition is Zeno's most famous paradox, a puzzle that has captivated philosophers and mathematicians for over 2 millennia. Zeno of Elea constructed this argument in the 5th century BCE as part of his defense of Parmenidean monism, the idea that reality is one unchanging whole and that motion and plurality are illusions. And the paradox was meant to show that the concept of motion leads to absurdity, that if we accept that space and time can be divided infinitely, then the faster can never overtake the slower. And since this conclusion is obviously false, something must be wrong with our assumptions about motion and change. The paradox rests on the idea that Achilles must complete infinitely many tasks, reaching the first point where the tortoise was, then the second, then the third, and so on without end. And if each task takes some amount of time, however small, then infinitely many tasks would require infinite time. And yet in reality, Achilles catches and passes the tortoise in a finite time. And so where is the error? Aristotle argued that the paradox confuses potential and actual infinity, that while the path can be divided into infinitely many segments in thought, Achilles does not actually perform infinitely many separate actions. He simply runs continuously and smoothly. And the infinite division is an artifact of analysis, not a feature of the motion itself. The resolution became clearer with the development of calculus, which showed that an infinite series of diminishing intervals can sum to a finite total, that 1 + 1/10 + 100th, and so on converges to a specific finite value. And so the infinite number of time intervals Achilles requires to reach each successive position also sum to a finite time, the time it takes him to overtake the tortoise. Yet the paradox retains a strange power, a sense that something about infinity remains counterintuitive, that the idea of completing an infinite number of steps feels impossible, even when mathematics insists it is not, and philosophers continue to debate whether the mathematical resolution truly captures the conceptual problem or merely sidesteps it. The paradox also connects to questions about the nature of space and time, whether they are continuous or discrete, whether motion is genuinely smooth or composed of tiny jumps, whether there is a smallest possible distance or duration beyond which reality cannot be divided. And these questions remain open in modern physics, where quantum mechanics and theories of spacetime suggest that the classical picture of smooth continuous motion may break down at the smallest scales. If you enjoy these explorations of paradox and the limits of thought, consider subscribing so you never miss a journey into philosophy's most perplexing puzzles, and perhaps leave a comment sharing where you are in the world as you listen to these ideas unfold. Achilles and the tortoise remain locked in their eternal race, a metaphor for the human attempt to reconcile the finite with the infinite, the continuous with the discrete, the logical with the intuitive. And the paradox endures as a reminder that even the simplest motion, a hero chasing a tortoise, conceals within it mysteries that have not been fully solved. Questions that linger at the boundary where mathematics meets reality, where reason meets experience, where what must be true, according to logic, clashes with what obviously is true, according to the world. Russell's paradox. In the year 1901, a young mathematician named Bertrand Russell discovered a contradiction so profound that it shattered the foundations of mathematics and forced an entire generation of logicians to rebuild their discipline from the ground up. And this contradiction became known as Russell's paradox, a simple question about sets that revealed a fatal flaw in the way mathematicians understood collections and categories. A set is merely a collection of objects, and sets can contain anything: numbers, colours, ideas, even other sets. And at first this seems harmless enough. A set of all chairs, a set of all prime numbers, a set of all books ever written. Some sets contain themselves as members and some do not. And this too seems straightforward. A catalogue of all catalogues would include itself because it is also a catalogue, while a list of all fruit does not include itself because a list is not a fruit. Russell posed a deceptively innocent question. Consider the set of all sets that do not contain themselves. Does this set contain itself? And the mind stumbles immediately into contradiction. If the set contains itself, then by definition it should not contain itself, because the rule states it only includes sets that do not contain themselves. But if it does not contain itself, then it must include itself, because it fits the criteria perfectly. And so the paradox loops without end, a perfect logical knot that cannot be untied. This was not merely a clever riddle or a philosophical curiosity, it was a disaster for mathematics, because at the time, mathematicians believed they could organize all of mathematical knowledge using set theory, a system proposed by Georg Cantor that treated sets as the fundamental building blocks of reality. But Russell's paradox proved that naive set theory was inconsistent, that it allowed contradictions to exist within its structure, and if contradictions are permitted, then anything can be proven true or false, rendering the entire system useless. Russell himself compared the paradox to a barber in a village who shaves all and only those men who do not shave themselves. And the question arises, does the barber shave himself? And if he does, then he should not, because he only shaves men who do not shave themselves. But if he does not, then he must, because he shaves all men who do not shave themselves. And the loop tightens again. Mathematicians scrambled to patch the damage, and various solutions emerged over the following decades. Zermelo and Frankel developed a new version of set theory that imposed strict rules about which sets could exist, forbidding the kind of self-reference that allowed Russell's paradox to form, while type theory introduced hierarchies that prevented sets from containing themselves by assigning different logical levels to different kinds of objects. Others embraced paraconsistent logic, systems that allow contradictions without collapse, or rejected the entire project of grounding mathematics in set theory, seeking new foundations altogether. Russell's paradox also influenced philosophy beyond mathematics, touching on questions of language, meaning, and self-reference, revealing that not all grammatically correct statements are logically coherent, that some sentences create traps from which reason cannot escape. The paradox appears in unexpected places. In computer science, where recursive definitions can cause programs to crash, in legal systems where laws reference themselves in contradictory ways, in everyday thought whenever categories attempt to classify themselves. It stands as a reminder that even the most rigorous systems of thought contain limits, that logic itself is not immune to paradox, that the quest for certainty and completeness may be forever haunted by statements that twist back on themselves and devour their own meaning. Synesthesia. Paradox: why numbers have colours and sounds have tastes. A person looks at the number 5 and sees it as blue, not imagines it as blue, not associates it with blue, but actually sees blue, experiences colour as an intrinsic property of the number. And another person hears music and tastes chocolate, hears certain chords, and the taste appears involuntarily, automatically. And these experiences are synesthesia, are cross-modal sensory experiences where stimulation in one modality produces perception in another, and synesthesia is not metaphor, is not learned association, is a genuine perceptual phenomenon experienced by roughly 4% of the population. And the paradox is that synesthetes experience properties that are not physically present, see colours that are not in the stimulus, taste flavours that have no source, and yet these experiences are consistent, are reliable. The same numbers always evoke the same colours, the same sounds always evoke the same tastes, and this reliability distinguishes synesthesia from imagination or association, shows that synesthesia is automatic, is perceptual rather than cognitive, and the phenomenon reveals something fundamental about how the brain is organised, shows that sensory modalities are not strictly separate, but can communicate, can influence each other, and synesthesia represents an extreme of this cross-modal interaction, represents a neural architecture where connections between sensory areas are stronger than normal, are sufficient to produce conscious experiences in one modality when another is stimulated. Imagine being a grapheme color synesthete, the most common form where letters and numbers evoke colors, and you read this text and every letter has its own color. A is red, B is green, C is yellow, and the colors are vivid, are as clear as real colors, are not vague or imagined but are perceptually present. And when you see the letter A, you cannot help but see red. The color is automatic, is triggered by the visual form of the letter, and this coloring happens for all letters and numbers, creates a richly colored experience of reading. And while this might sound beautiful, it can also be distracting, can interfere with reading when the printed colors conflict with synesthetic colors, can create confusion. And yet for synesthetes, this is normal, is how the world has always looked. And they are often surprised to learn that others do not experience letters as colored, that the colors are unique to synesthetes. Synesthesia demonstrates that perception is not modular, is not strictly segregated by sensory modality, and in synesthetes there is cross-activation. There are connections between sensory areas that do not exist or are weaker in non-synesthetes, and these connections allow activity in one area to trigger activity in another. And when grapheme area, the region that processes letter and number shapes, is activated, it also activates color area, the region that processes color, and this cross-activation produces the experience of colored letters. And neuroimaging studies have confirmed this, have shown that when synesthetes see numbers, color areas of visual cortex are activated, are lit up, and this activation is automatic, is bottom-up, is not produced by conscious thought or imagination, but is triggered by the stimulus itself. Visualize the brain as having sensory areas that are normally separate: visual area, auditory area, taste area, and these areas process their respective inputs and pass information to higher level regions. But in synesthetes, there are additional connections. There are pathways between sensory areas that allow direct crosstalk, and these pathways are the neural basis of synesthesia, are what allows stimulation in one modality to produce experiences in another. And the connections are not learned, are not created through experience, but are developmental, are present from early life. And synesthesia is lifelong, is consistent. The same cross-modal experiences occurring throughout the synesthete's life. The synesthesia paradox is that these experiences are perceptual, are as real as any other perception, and yet the properties perceived are not present in the stimulus. The number 5 is not blue, is black on white, and yet the synesthete sees blue. And this challenges theories that say perception is veridical, is accurate, is a representation of physical reality. And synesthesia shows that perception can include properties that are not in the world, that are generated internally, and yet these properties feel external, feel like properties of objects rather than like internal mental states. And this raises questions about the nature of perception, about what it means for perception to be of something, about whether all perception involves some degree of construction, some degree of adding properties that are not in the stimulus. One theory of synesthesia is that everyone is born with extensive cross-modal connections, that infant brains have connections between all sensory areas, and during development, most of these connections are pruned or eliminated, and sensory areas become more segregated. And in synesthetes, some of these early connections are preserved, are not pruned, and this preservation allows the cross-modal experiences to continue into adulthood. And this theory is supported by evidence that infants show some synesthetic effects, show cross-modal correspondences, and that synesthesia runs in families, has a genetic component, suggesting that genes that regulate synaptic pruning are involved. Another theory is that synesthesia involves disinhibition, involves normally present connections between sensory areas that are usually inhibited, are suppressed, and in synesthetes this inhibition is weakened, is less effective, and so the connections are active, allow cross-activation, and this theory is supported by evidence that synesthesia can be induced temporarily in non-synesthetes through drugs that reduce inhibition, through hypnosis, through sensory deprivation, suggesting that the neural machinery for synesthesia is present in everyone, but is normally inhibited, and synesthetes have less inhibition, have more open channels between sensory areas. Synesthesia also has practical implications. Some synesthetes report that their experiences are useful, provide memory aids, make information more distinctive, easier to remember, and some musicians with sound-colour synesthesia report that the colours help with composition, with understanding musical structure, and some artists deliberately cultivate synesthetic experiences, use them as sources of creativity. And understanding synesthesia has implications for education, for recognizing that people process information differently, that sensory experiences vary across individuals, and that teaching should accommodate these differences, should recognize that some students have richly colored experiences of letters and numbers, while others do not. The phenomenon also raises questions about consciousness, about qualia, about the subjective properties of experience, because synesthetes have different qualia than non-synesthetes, have colour experiences that others do not, and this shows that consciousness is not uniform, is not the same across individuals, and qualia vary, and this variation is not just quantitative, is not just more or less of the same experience, but is qualitative, involves entirely different types of experience, and this challenges theories that say consciousness is universal, is the same for everyone, and supports theories that say consciousness is individual, is constructed by each brain in potentially different ways. And synesthesia is one example of this variation, is one way that consciousness can differ. Some philosophers argue that synesthesia shows that perception is not representational, does not represent external properties, because the colours seen by graphema colour synesthetes do not represent anything in the world. The number 5 is not blue, and yet the colour is perceived, and this challenges representational theories of perception, suggests that perceptual experiences are not always representations of external properties but can be internally generated responses. And synesthesia is a case where the response includes properties that are not being represented, and this raises questions about what makes perception representational, whether all aspects of perception are representations or whether some are merely responses are produced by the perceptual system without representing anything external. The number appears black on white, and the synesthete sees blue, vivid, and automatic. The colour is as real as the number, is as perceptually present, and yet the colour is not there, is not in the stimulus, is generated by the brain, is a cross-modal activation, and the synesthesia paradox remains. Perception includes non-veridical properties, includes experiences that do not correspond to stimulus properties, and yet these experiences are automatic, are reliable, are as perceptually real as any other, and synesthesia endures as one of the most fascinating phenomena in neuroscience, a demonstration that sensory modalities are not strictly separate, that cross-modal connections exist, that perception can include internally generated properties, and that consciousness varies across individuals, includes experiences that are unique, that are not shared by everyone, and the colours remain overlaid on letters, triggered by sounds, evoked by tastes, and the cross-modal world of synesthetes continues, different from the world non-synesthetes perceive, richer in some ways, more confusing in others, and the phenomenon persists. The Allais paradox. Maurice Allais, a French economist and Nobel laureate, presented a pair of choices in 1953 that revealed a systematic pattern of preferences violating the independence axiom of expected utility theory, and this became known as the Allais paradox, one of the most influential demonstrations that human decision-making deviates from the prescriptions of standard rational choice theory. And the paradox shows that people's preferences can be influenced by irrelevant alternatives, by outcomes that occur in both options and should therefore cancel out, yet somehow affect which option is chosen. The first choice involves two lotteries. Lottery A offers a certain gain of $1 million, while Lottery B offers a 10% chance of winning $5 million, an 89% chance of winning $1 million, and a 1% chance of winning nothing. And when faced with this choice, most people prefer Lottery A, the certain million, preferring the sure thing to the gamble, even though the gamble has a higher expected value. And this preference reflects risk aversion, a common and generally accepted feature of human decision-making. The second choice involves two different lotteries. Lottery C offers an 11% chance of winning $1 million and an 89% chance of winning nothing, while Lottery D offers a 10% chance of winning $5 million and a 90% chance of winning nothing. And when faced with this choice, most people prefer Lottery D, the gamble with the higher potential payoff, accepting the slightly lower probability of winning in exchange for the much larger prize. The paradox emerges when these two preference patterns are analysed together, because the independence axiom of expected utility theory requires that if Lottery A is preferred to Lottery B, then Lottery C should be preferred to Lottery D. And the reason is that Lotteries A and B differ from Lotteries C and D only in that there is an 89% chance in both A and B of receiving $1 million, and in both C and D this 89% outcome is replaced with winning nothing, and this replacement should affect both lotteries equally, should not change the preference order, because the independence axiom says that preferences between lotteries should depend only on outcomes where the lotteries differ, not on outcomes that are the same in both. And the 89% probability mass is shifted in the same way for both pairs, and so if you prefer A to B, you should also prefer C to D. And if you prefer D to C, you should also prefer B to A. The typical pattern of preferences, A over B and D over C, cannot be represented by any utility function satisfying the expected utility axioms. And so the Allais paradox demonstrates that people systematically violate the independence axiom, that their preferences are sensitive to common outcomes in ways that expected utility theory does not permit. And this violation is robust, appearing in experiments with diverse populations, with real monetary stakes, with careful experimental design, and the paradox cannot be dismissed as error or confusion, but represents a genuine feature of human decision-making. The paradox has inspired alternative theories that can accommodate the observed preferences, including prospect theory, developed by Daniel Kahneman and Amos Tversky, which modifies expected utility theory by introducing reference points, by treating gains and losses differently, by allowing for probability weighting where people overweight small probabilities and underweight large probabilities. And these modifications can explain the Allais preferences, because in the first choice, the certainty of $1 million receives extra weight, making Lottery A more attractive, while in the second choice the small probabilities are overweighted, making the 10% chance of $5 million in Lottery D seem more appealing than the 11% chance of $1 million in Lottery C. Other theories include regret theory, where people anticipate the regret they would feel if they made the wrong choice. And this anticipated regret influences preferences in ways that violate independence, because the certain million in Lottery A avoids the regret of choosing the gamble and losing everything, while the choices between C and D do not have this asymmetry. And rank-dependent utility theory, which generalizes expected utility by allowing the utility of lotteries to depend not just on outcomes and probabilities, but on the rank ordering of outcomes, and this allows for preferences that violate independence while maintaining other desirable properties. The Allais paradox raises normative questions about rationality. Some argue that the independence axiom is a fundamental requirement of rational choice, that violating it leads to incoherence, to preferences that can be exploited through Dutch books, or money pumps, to decision-making that is systematically suboptimal, and that people who exhibit alley preferences are making mistakes and should revise their preferences to conform to expected utility theory. While others argue that the independence axiom, while mathematically convenient, is not a necessary condition for rationality, that it does not capture important aspects of how people value uncertain prospects, that preferences like those in the alley paradox reflect legitimate concerns about certainty, regret, and the context of choice, and that we should revise our normative theories to accommodate these preferences rather than dismissing them as irrational. The paradox also has practical implications for economics and policy, because if people systematically violate independence, then markets may not function as standard theory predicts. Risk preferences may be context-dependent. Insurance and investment decisions may be influenced by framing effects, and policies designed to maximize expected utility may not align with what people actually prefer. And understanding these deviations from expected utility helps explain phenomena like the equity premium puzzle, the disposition effect, and other anomalies in financial markets and economic behavior. The lotteries sit before you, the choices must be made, and your preferences, revealed through your choices, tell a story about how you value certainty and risk, about how you weigh probabilities and outcomes, and the story violates the axioms of rational choice, violates the clean mathematical structure of expected utility theory, and yet the choices feel reasonable, feel justified, feel like they reflect something important about value and uncertainty that the theory misses, and the paradox persists. The gap between theory and behavior remains. The independence axiom is violated again and again in experiments and in life, and decision theorists must choose. Either insist that the axiom is normatively binding and that violators are irrational, or acknowledge that the axiom is too strong, that rational choice is more complex than expected utility allows, and that new theories are needed to capture the richness of human decision-making. And the Allais paradox remains a landmark, a decisive demonstration that classical rational choice theory does not fully describe or prescribe human behavior, a challenge that spawned new theories and new research programs, and a reminder that rationality is contested, that what counts as a reasonable choice depends on assumptions and frameworks that are themselves open to question, and the lotteries remain, the choices remain, the preferences remain, and the paradox endures, unsolved in the sense that no consensus has emerged about whether the preferences are rational or irrational, about whether we should revise our theories or our preferences, about whether independence is a negotiable axiom or a non-negotiable requirement. And the debate continues. Philosophers and economists and psychologists arguing about what rationality requires, about what humans actually do, and about the relationship between these two questions. Quine's Gavagai problem: why we can never know what anyone really means. An anthropologist arrives in a remote village to study an unknown language, a language no outsider has encountered before. And the anthropologist has no translator, no dictionary, no common linguistic framework, only observations and patience, and the method is radical translation. Learning the language from scratch by observing how natives use words in response to events. And one day, a rabbit runs past and a native points and says Gavagai, and the anthropologist writes in the notebook, Gavagai means rabbit. And this seems reasonable, seems like an obvious inference. The native saw a rabbit and said Gavagai, so Gavagai must refer to rabbits. But philosopher Willard Van Orman Quine points out a problem, a deep problem about meaning and translation. Because Gavagai might mean rabbit, but it might also mean undetached rabbit part, or rabbit stage, or collection of rabbit molecules, or instance of rabbithood. And all these translations are consistent with the native's behaviour. All would lead the native to say Gavagai in exactly the same circumstances, whenever a rabbit is present, and there is no fact of the matter, no objective truth about which translation is correct. No way to determine what Gavagai really means. And this indeterminacy is not due to practical limitations, not due to insufficient evidence, but is fundamental, is a consequence of how meaning works. And this is Quine's Gavagai problem, also called the problem of indeterminacy of translation, a challenge to the idea that words have determinate meanings, that translation has right answers, and that we can know what others mean when they speak. Imagine trying to distinguish between Gavagai means rabbit and Gavagai means undetached rabbit part. And you point to the rabbit and the native says Gavagai, and you point to the rabbit's ear and ask whether this is Gavagai, and the native responds, but you do not know whether the response means yes because the ear is an undetached rabbit part, or no, because the ear is not a whole rabbit, or something else entirely. And every test you design, every question you ask, can be interpreted in multiple ways, can be answered consistently by multiple translations, and no amount of observation, no behavioural evidence can definitively settle which translation is correct, because the native's behaviour under all possible circumstances is compatible with multiple interpretations. And Quine argues that this shows meaning is indeterminate, that there is no fact about what Gavagai really means, only different translation manuals that work equally well, that map the native's language onto ours in different but equally legitimate ways. The problem generalizes beyond anthropology to all understanding of language, because even when we share a language, even when we both speak English, the Gavagai problem applies. We cannot be certain that we mean the same thing by our words, that rabbit means to you what it means to me. We might be using different concepts, carved up differently, but our behavior is similar enough that we never notice the difference. And this raises the disturbing possibility that communication is always partial, always approximate, that we never fully understand each other, that meaning is not something objective that words have, but something we impose through interpretation, and different interpretations can fit the evidence equally well, and there is no transcendent perspective from which to judge which interpretation is correct. Visualize meaning as a relationship between words and world, and Quine's point is that this relationship is underdetermined by behavior, by the evidence available to translators, because infinitely many relationships are consistent with the same behavioral evidence. Infinitely many ways of mapping words to world produce the same observable patterns, and choosing among these possibilities requires going beyond evidence, requires making decisions that are not forced by facts, and these decisions constitute meaning rather than discovering it. And so meaning is partially conventional, partially stipulated, not fully determined by reality. The Gavagai problem challenges referential theories of meaning, theories that say words mean things because they refer to objects in the world, because rabbit refers to rabbits, and water refers to water, and Quine's argument shows that reference is inscrutable, cannot be determined from behaviour alone, because words can be interpreted as referring to different things, different ways of carving up reality, and all interpretations fit the evidence, and so reference is not an objective relation, but is relative to a translation manual, relative to a scheme of interpretation, and different manuals. Different schemes can assign different references to the same words while remaining equally correct. One response to the Gavagai problem accepts the indeterminacy, embraces it as a truth about meaning, argues that Quine is right, that there is no fact of the matter about what words mean beyond what is determined by behavioural evidence, and meaning is holistic, depends on the entire network of beliefs and language practices. And translation manuals are theoretical frameworks that organise this evidence. And like all theories, they are underdetermined by data, and multiple theories fit the same data equally well. And choosing among them involves pragmatic considerations, simplicity, utility, coherence, but not truth in any absolute sense. And this response treats meaning as a human construction, something we create through practices rather than something we discover in nature. Another response denies the indeterminacy, argues that Quine's thought experiment is artificial, that in real translation situations additional evidence is available, evidence about intentions, about how speakers correct each other, about the structure of their conceptual schemes. And this additional evidence narrows down the possibilities, rules out bizarre interpretations like undetached rabbit part, and determines that gavagai means rabbit in the ordinary sense. And while perfect certainty may be impossible, practical determinacy is achievable, and meaning is objective enough for communication to succeed, for translation to have right and wrong answers. And the gavagai problem is an epistemological worry, a concern about how we know what words mean, but it does not show that words lack determinate meanings, only that discovering those meanings is difficult. A third response appeals to charity, to the principle that we should interpret speakers as making sense, as having coherent beliefs, as speaking truly most of the time. And this principle constrains translation, rules out interpretations that make speakers irrational or massively mistaken. And while charity does not uniquely determine translation, it narrows the range of acceptable interpretations, and combined with simplicity and other pragmatic virtues, it makes translation tractable, makes it possible to arrive at good translations, even if not perfect ones. And this response treats translation as an interpretive practice, guided by norms rather than as a purely empirical investigation, guided only by behaviour. The gavagai problem also connects to broader philosophical issues about realism and anti-realism, about whether there are objective facts independent of our theories and languages. Because if meaning is indeterminate, then perhaps reality itself is indeterminate. Perhaps there is no fact about whether rabbits or undetached rabbit parts exist, only different ways of organising experience, different conceptual schemes that carve up the world differently. And Quine's ontological relativity, his claim that what objects exist is relative to a language or theory, follows from the gavagai problem, from the recognition that reference is inscrutable, that we cannot say what exists absolutely, but only what exists relative to a framework. The anthropologist sits with a notebook, the word gavagai recorded, the translation uncertain, and the native speaks, and the anthropologist interprets, and communication proceeds approximately, pragmatically, successfully enough for practical purposes, and whether gavagai really means rabbit or something else remains undetermined, remains a question without an answer. And Quine's problem persists, not as a practical obstacle to translation, but as a philosophical challenge to theories of meaning, as a demonstration that meaning is more elusive than we thought, more dependent on interpretation and less determined by facts. And the gavagai problem endures as one of Quine's most influential contributions, a thought experiment that changed how philosophers think about language, about meaning, about translation, and about the relationship between words and world. And the problem remains unsolved, perhaps unsolvable, a permanent feature of linguistic philosophy, a reminder that understanding each other is harder than it seems, that meaning is indeterminate, that communication is an achievement rather than an automatic consequence of shared language, and that the gap between what we say and what we mean, between our words and their reference, can never be fully closed. And the rabbit runs past and the native says, gavagai, and we translate approximately, hopefully, never quite certain that we have understood. The analysis paradox. Philosophy has long been concerned with analysis, with taking complex concepts and breaking them down into simpler components, with providing definitions that specify the necessary and sufficient conditions for the application of a term. And this project of conceptual analysis seems both important and straightforward. We want to know what knowledge is, what justice is, what truth is, and we proceed by analysing these concepts, by stating explicitly what they mean, by giving definitions that capture their essential features. Yet there is a paradox lurking here, a puzzle about whether analysis is even possible. And this is the paradox of analysis. first articulated clearly by C.H. Langford and discussed extensively by G.E. Moore and others in the early 20th century. The paradox can be stated simply: suppose we offer an analysis of some concept. For example, we might analyze the concept brother as male sibling, and this analysis, if correct, should be informative, should tell us something we did not already know about what brotherhood consists in, should illuminate the concept by making its structure explicit. But if the analysis is correct, then the analysandum, the concept being analysed, and the analysans, the analysis itself, must have the same meaning. They must be synonymous, otherwise the analysis would be incorrect. It would not capture what brotherhood really is. And if they are synonymous, then the statement brother means male sibling should be trivial, should be like saying brother means brother, a mere tautology that provides no new information. And so the analysis cannot be both correct and informative. If it is correct, then it is trivial. And if it is informative, then it is not a genuine analysis, but merely a stipulation or a proposed change of meaning. The paradox threatens the entire project of conceptual analysis, because it suggests that analysis cannot do what it is supposed to do, cannot both correctly identify the meaning of a concept and provide new insight into that meaning, cannot be both true and interesting. And so either conceptual analysis is impossible, or our understanding of what analysis is and what it aims to achieve must be revised. One response to the paradox distinguishes between sense and reference, between the meaning of a term and what it picks out, and argues that an analysis can be informative even if the analysandum and analysans refer to the same thing, because they can differ in sense, in the way they present or describe that thing. And so the analysis brother means male sibling is informative, because even though brother and male sibling refer to the same set of individuals, they present that set in different ways, one as a family relation and the other as a combination of gender and kinship. And this difference in sense makes the identity statement informative rather than trivial. Another response appeals to a distinction between conceptual and factual knowledge, arguing that analysis does not provide factual knowledge about the world, but conceptual knowledge about our own concepts, that it makes explicit what was already implicit in our understanding, that it brings to consciousness the structure of concepts that we already possess and use, but have not fully articulated. And so, the informativeness of analysis is not the informativeness of discovering new facts, but the informativeness of self-clarification, of making our own conceptual commitments explicit and transparent. A third response associated with Quine and others skeptical of the analytic-synthetic distinction denies that there is a sharp line between conceptual analysis and empirical investigation, arguing that all beliefs form a holistic web where conceptual revisions and factual discoveries are intertwined, and that what we call analysis is really just careful reflection on our current best theory of the world, subject to revision in light of new evidence or theoretical considerations. And on this view, the paradox dissolves, because analysis is not supposed to be a priori or purely conceptual, but is continuous with empirical inquiry, and so it can be both correct and informative without any mystery. The paradox also raises questions about the methodology of philosophy, about whether philosophy can make progress through analysis or whether some other method is needed. And different philosophical traditions have taken different stances, with analytic philosophy traditionally emphasizing conceptual analysis as a central tool, while continental philosophy has been more skeptical of analysis, focusing instead on interpretation, critique, and phenomenological description. And the paradox of analysis has been one factor driving some philosophers away from traditional analysis toward other approaches. The paradox connects to issues about understanding and competence, because we seem to have a kind of implicit or tacit understanding of concepts like knowledge, justice, and truth. We can use these concepts correctly, can apply them to particular cases, can recognize when they're used inappropriately, And yet when asked to state explicitly what these concepts mean, to provide a definition, we struggle. And this suggests that conceptual competence does not require explicit knowledge of definitions, that understanding can be practical and procedural rather than theoretical and propositional, and that analysis attempts to convert implicit understanding into explicit knowledge, a conversion that is difficult and perhaps impossible to complete without remainder. The paradox also appears in the context of philosophical disagreement, because philosophers have been offering analyses of key concepts for millennia, and yet consensus remains elusive. Different philosophers provide different analyses of knowledge, of justice, of truth, and it is not always clear how to adjudicate between competing analyses, whether by appeal to intuitions about particular cases, by considerations of theoretical simplicity and fruitfulness, or by some other standard, and the lack of agreement raises the question of whether these concepts have determinate meanings that analysis can discover, or whether they are vague, contested, or essentially contested, such that no single analysis could capture all the ways they are legitimately used. The analysis paradox remains a puzzle at the heart of philosophy, a question about what philosophy is doing when it offers definitions and analyses, whether it is discovering pre-existing meanings, stipulating new ones, or engaging in some more complex activity that combines elements of discovery, stipulation, and rational reconstruction, and the paradox has not been definitively resolved. Different philosophers find different responses more or less compelling, and the debate continues, with implications for how we understand the nature and methods of philosophical inquiry. And the concept sits there, waiting to be analysed, inviting us to state its essence, to specify its conditions, to make explicit what we already implicitly know, and yet the analysis, when offered, seems either to tell us nothing new or to change the subject, to offer a different concept rather than clarifying the original one. And the paradox persists, a thorn in the side of analysis, a reminder that understanding is more elusive than it appears, that the gap between knowing how to use a concept and knowing what it means is wider than we thought, and that philosophy, despite its ancient commitment to clarity and definition, to making the implicit explicit and the confused clear, may be chasing a goal that is inherently problematic, inherently paradoxical, a goal that recedes as we approach it, that becomes more obscure the more we try to illuminate it, and yet we continue to analyse, to offer definitions, to seek clarity, because the alternative, giving up on understanding, seems worse. Olbers's paradox, why the night sky is dark when it should blaze with light. Look up at the night sky and you see darkness, scattered stars against a black background, empty space between the points of light. And this seems natural, seems obvious. The sky's dark because there are not many stars, because most of space is empty. But in an infinite, eternal universe filled with stars, this darkness becomes paradoxical, becomes something that should not exist. And this is Olbers' paradox, named after German astronomer Heinrich Wilhelm Olbers, who discussed it in 1823, though the puzzle was recognized earlier by others, including Johannes Kepler and Edmund Halley. And the paradox asks why the night sky is dark, when simple reasoning suggests it should be blazing bright as the surface of the sun in every direction. The argument proceeds as follows. If the universe is infinite in spatial extent and has existed forever, and if stars are distributed roughly uniformly throughout this infinite space, then every line of sight from Earth, extended far enough, must eventually intersect the surface of a star, because in an infinite universe, with infinite stars, every direction contains a star somewhere along that sight line, perhaps nearby or perhaps trillions of light years away, but somewhere, and so the entire sky should be covered with stellar surfaces, should glow with the brightness of a star, and there should be no dark spaces, no black background, only light. And yet we see darkness. We see mostly empty space with occasional bright stars. And this contradiction is Olbers' paradox. Visualize the reasoning more carefully. Imagine dividing the universe into concentric shells around Earth, like layers of an onion, each shell at a different distance, and count how many stars are in each shell. A shell at distance r has volume proportional to r squared times the shell thickness, because the surface area of a sphere grows as r squared. And if stars are uniformly distributed, then the number of stars in the shell is proportional to r squared. But the brightness of each individual star falls off as 1 over r squared due to the inverse square law of light. Light spreads out as it travels, and so the total brightness contributed by all stars in a given shell is the number of stars times the brightness per star, which is r squared times 1 over r squared. And these factors cancel, and each shell contributes the same total brightness regardless of distance. And since there are infinitely many shells in an infinite universe, the total brightness is infinite, and the sky should be infinitely bright. And even if we account for stars blocking each other, eventually every sight line intersects a star, and the sky should glow uniformly with the brightness of stellar surfaces. The resolution of Olbers' paradox involves recognizing that the universe is not infinite and eternal in the way the paradox assumes. Modern cosmology tells us that the universe has a finite age, about 13.8 billion years, and light travels at a finite speed, and so we can only see light from stars within our observable horizon, stars whose light has had time to reach us. And this limits the number of stars we can see. And more importantly, the universe is expanding, and distant stars are receding from us, and their light is redshifted, stretched to longer wavelengths and lower energies by the expansion of space. And this redshift dims distant starlight. And for sufficiently distant stars, the redshift is so extreme that their light is shifted into the infrared or radio spectrum, invisible to our eyes. And the combination of finite age and cosmological expansion means that only a finite amount of starlight reaches us, and the night sky is dark. Not because stars are sparse, but because the universe has not existed long enough for light from all stars to reach us, and because expansion dims the light from distant sources. Another factor is the finite lifetime of stars. Stars are not eternal. They form, they shine for millions or billions of years, and they die. And in a finite age universe, not all regions have had time to form stars, and not all stars have been shining throughout cosmic history, and so the background radiation from stars is further reduced. And these factors combine to ensure that the night sky is dark despite the vast number of stars in the universe. The paradox also touches on thermodynamics and equilibrium, because if the universe were infinite, eternal, and static, with stars distributed uniformly, then eventually the radiation from all these stars would fill space uniformly. Space would reach thermal equilibrium with stellar surfaces, and everything would be at the same temperature as the surface of a star, about 6,000 degrees Kelvin, and Earth would be vaporized, life would be impossible, and the darkness of the night sky is evidence that the universe is not in thermal equilibrium, is not static and eternal, but is instead dynamic, expanding, and young. Olbers' paradox played a role in the development of modern cosmology. It was one piece of evidence that the universe cannot be static and eternal, that something must be different about the large-scale structure of space and time. And when Edwin Hubble discovered in the 1920s that the universe is expanding, that distant galaxies are receding from us, this provided a natural resolution to Olbers' paradox. The expansion redshifts and dims distant light, preventing the accumulation of infinite brightness, and the finite age of the universe, confirmed by observations of the cosmic microwave background and the distribution of galaxies, completes the resolution, ensuring that we see only a finite amount of cosmic history, only the light from stars within our past light cone. The paradox also has poetic resonance. It asks why there is darkness, why night exists, why space is not filled with light. And the answer is that darkness is a consequence of time and change, of the universe having a beginning, of stars being born and dying, of space expanding and carrying light away, and darkness becomes not an absence, but a presence, not a void, but a canvas. Evidence of cosmic history, evidence of the dynamic evolving universe we inhabit, and the dark night sky, far from being empty or boring, is rich with information. Tells us about the finite age of the cosmos, about the expansion of space, about the distribution and evolution of stars and galaxies, and Olbers' paradox, resolved but not forgotten, remains a reminder that even simple observations, like the darkness of night, can contain profound mysteries, can require deep theories to explain, and can reveal fundamental truths about the nature of the universe. The stars shine against the darkness, scattered lights in an empty sky, and the darkness itself is meaningful, is informative, is the signature of a finite age expanding universe. And Olbers' paradox, resolved by modern cosmology, endures as a teaching tool, as an illustration of how seemingly simple questions can have complex answers, and as a monument to the human capacity to wonder about the ordinary, to see puzzles where others see only the familiar, and to pursue those puzzles until the universe reveals its secrets. Nagel's bat problem: why you can never know what it's like to be anything else. A philosopher contemplates a bat hanging upside down in a cave, navigating through echolocation, emitting high-frequency sounds and listening to the echoes, building a sonic map of the world. And the philosopher asks what it is like to be a bat. What is the subjective character of bat experience? What does echolocation feel like from the inside? And philosopher Thomas Nagel argues that no amount of objective information about bat neuroscience, about bat behavior, about the physics of sonar, can tell us what bat experience is like, because subjective experience has an essential first-person character, a what it is likeness that cannot be captured from the third-person objective perspective of science, and the gap between objective description and subjective experience is unbridgeable. And this means that consciousness, at least in its subjective aspect, resists scientific explanation, resists reduction to physical terms. And this is Nagel's bat problem, presented in his famous 1974 paper, What Is It Like to Be a Bat? And the problem illustrates the explanatory gap between physical facts and phenomenal facts, shows that subjective experience involves something that objective science cannot capture, and challenges physicalist theories of mind to explain how subjective character could be accommodated within a purely physical framework. Imagine trying to know what echolocation is like, trying to understand bat experience from the inside, and you learn all the objective facts. Learn about the bat's auditory system, about how it processes echoes, about which brain regions are involved. And this knowledge is real, is valuable, tells you how echolocation works, but it does not tell you what it feels like, does not give you access to the bat's subjective experience, to the phenomenology of navigating by sound. And Nagel's point is that this gap is not due to practical limitations, not due to insufficient technology or incomplete knowledge, but is a fundamental gap between objective and subjective perspectives, between what can be known from outside and what can only be known from inside. And no amount of objective knowledge can bridge this gap, can provide access to subjective experience. The bat problem generalizes beyond bats to any creature with a different sensory modality, a different nervous system, a different form of consciousness. And Nagel uses bats because they are mammals, are relatively similar to humans, yet have a sensory mode, echolocation, that humans lack. And this combination makes the example vivid, makes the gap between human and bat experience clear. And if we cannot know what it is like to be a bat, then we certainly cannot know what it is like to be a fish, an insect, an octopus, creatures whose nervous systems and sensory worlds are even more alien. And this suggests that consciousness, in its subjective aspect, is fundamentally private, is accessible only to the being who has it, and different kinds of consciousness are mutually inaccessible, cannot be fully understood from outside. Visualize the subjective character of experience as the view from inside, the first-person perspective, the what it is likeness. And this perspective is essential to consciousness, is what makes consciousness consciousness rather than merely information processing. And Nagel argues that physicalism, the view that everything is physical, must either deny that subjective character exists, which seems false because we all know from our own case that consciousness has a subjective character, or must explain how subjective character could be physical, how objective physical facts could constitute subjective, first-person experiences. And this explanation is what physicalism has not provided, what the bat problem challenges physicalism to provide. One response to the bat problem accepts the explanatory gap, but denies that it shows anything metaphysical, argues that the gap is merely epistemological, is about the limits of what we can know rather than about the nature of reality, and consciousness might be physical, even though we cannot fully understand it from the objective third-person perspective. And just as we cannot know what it is like to be a bat, we also cannot know what it is like to be another human, cannot fully access their subjective experiences, and yet we do not conclude that human consciousness is non-physical. And so the bat problem shows limits of knowledge, but not limits of physicalism, shows that subjective experience has aspects that resist objective description, but not that these aspects are non-physical. Another response argues that future science might bridge the gap, might develop ways of understanding subjective character objectively, might create theories that capture phenomenology in physical terms, and our current inability to imagine how this could be done does not prove that it cannot be done. And Nagel's argument trades on current ignorance, assumes that the gap is permanent when it might be merely temporary, and this response is optimistic about the prospects for physicalist explanations of consciousness, believes that the hard problem and the bat problem will eventually be solved by scientific progress. A third response from Nagel's position argues that the bat problem reveals something deep about the structure of reality, that consciousness has an irreducibly subjective aspect, an aspect that cannot be captured by objective physical description. And this does not mean consciousness is non-physical in the sense of being immaterial or supernatural, but it means that physicalism, as traditionally conceived, is incomplete, misses something essential about consciousness. And a complete theory of reality must include both objective physical facts and subjective phenomenal facts. And these two kinds of facts cannot be reduced to each other. And this position is sometimes called naturalistic dualism, accepts that consciousness is natural, is part of the natural world, but denies that it is reducible to physics. The bat problem also has implications for artificial intelligence, for whether machines could be conscious, because if we cannot know what it is like to be a bat, then we also cannot know what it is like to be a computer, cannot know whether AI systems have subjective experiences, and the bat problem suggests that behavioral evidence is insufficient, that even if a machine passes every behavioral test, exhibits intelligence, responds appropriately to stimuli, we still cannot know whether there is something it is like to be that machine, whether there is subjective experience behind the behavior, and this creates a permanent epistemic barrier, a limit on what we can know about machine consciousness. The bat hangs in the cave, emitting sounds, perceiving the world through echoes, and its experience is alien, is inaccessible to human understanding. And Nagel's question remains, what is it like? And the answer is we do not know, cannot know, because knowing requires access to the subjective perspective, requires being the bat or having the bat's sensory and cognitive capacities, and neither is possible. And so bat consciousness remains a mystery, remains forever beyond human comprehension. And this mystery is not unique to bats but applies to all consciousness, to the fundamental subjectivity of experience, to the what it is likeness that defines phenomenal consciousness. And Nagel's bat problem endures as one of the most influential thought experiments in philosophy of mind, a vivid illustration of the explanatory gap, a challenge to physicalist theories, and a reminder that consciousness, in its subjective aspect, resists objective description, resists scientific reduction, and remains one of the deepest puzzles about the nature of mind and reality. And the bat flies through the cave, navigating by sound, living its bat life, having its bat experiences, and what those experiences are like remains unknown, remains unknowable. And the problem persists, the gap between objective knowledge and subjective experience, the difference between knowing about consciousness and knowing consciousness from the inside. And Nagel's question echoes, what is it like to be a bat? And no answer comes, no answer can come, and the problem stands as a permanent marker of the limits of objective understanding, the irreducible subjectivity of experience and the mystery at the heart of consciousness. The Abilene Paradox: why groups choose what nobody wants. A family sits on a porch in Coleman, Texas, on a hot afternoon, comfortable, playing dominoes, and the father-in-law suggests driving to Abilene for dinner, 53 miles away in a car without air conditioning. And the suggestion is not enthusiastic, is tentative, but the son-in-law says sure, sounds good, not because he wants to go, but because he assumes others want to go, and he wants to be agreeable. And the wife says yes if you all want to go, and the mother-in-law says of course, and they all pile into the car and drive to Abilene in dusty heat, arrive hot and tired, eat mediocre food, drive back exhausted, and sitting on the porch again, someone admits they didn't really want to go, and then everyone admits they didn't want to go, admits they only agreed because they thought others wanted it, and the entire group took an action that no individual wanted, chose an outcome that everyone preferred to avoid. And this is the Abilene Paradox, described by management professor Jerry Harvey, a phenomenon where groups make decisions that contradict the preferences of all members, where collective action diverges from individual preferences, not through majority rule or compromise, but through misperception, through failure to communicate, through assumptions about what others want. And the paradox reveals that agreement is not always consensus, that unanimous decisions can be unwanted by everyone. And the Abilene Paradox shows a different kind of collective irrationality from Condorcet cycles or voting paradoxes. Shows irrationality that arises from social dynamics, from conformity pressure, from reluctance to dissent. And the paradox remains relevant for understanding group decision-making, for recognizing that groups can fail not just through conflict, but through false consensus, through everyone going along with what nobody wants. Imagine the psychology of each family member. Each sits on the porch comfortable, each prefers staying home, but each hears the suggestion and thinks, well, if someone is suggesting it, they must want it. I don't want to be the one who ruins everyone's plans. I should be agreeable, go along, be a team player. And so each agrees despite preferring to stay, and no one voices their actual preference. No one says I'd rather stay home. And the group collectively creates a false impression, creates the appearance of consensus when none exists, and everyone interprets others' agreement as reflecting genuine preference rather than social accommodation. And this mutual misperception drives the group toward an outcome no one wants. And the paradox unfolds, the trip is taken, the unwanted dinner eaten, and only afterward does truth emerge. Does communication clarify that everyone preferred staying home? And the group confronts the absurdity, the recognition that they did something no one wanted through failure to communicate authentically. The Abilene Paradox differs from groupthink, where group members genuinely conform their preferences to the group, genuinely come to believe the group view. And Abilene involves no genuine preference change, involves only misperception, only assumption about what others want. And members maintain their private preferences, but suppress them out of social pressure, out of desire to be agreeable. And this suppression is the source of the paradox, creates the gap between public agreement and private preference, and the gap allows groups to pursue actions that everyone opposes. And breaking the paradox requires someone to voice dissent, to say, actually, I'd prefer not to go. And this dissent can reveal that others feel the same, can break the false consensus, but dissent is risky, is socially uncomfortable, requires challenging what appears to be group preference. And most people avoid this, prefer to go along, and the paradox persists. Visualize the Abilene paradox as a coordination failure, where the optimal outcome requires everyone to reveal their true preferences, requires honest communication, but social norms and psychological tendencies prevent this, create pressure toward agreement, toward accommodation, toward not rocking the boat. And these pressures are strongest when relationships matter, when group harmony is valued, when dissent risks social costs and family dinners and work teams and community groups all face Abilene risks. All can make decisions that no one wants, through false consensus, through failure to communicate authentically. And the paradox shows that agreement is not always good, that unanimous decisions can be wrong, that groups need mechanisms for authentic communication, need cultures that encourage dissent, need permission to disagree. One lesson from the Abilene paradox is the importance of honest communication, of creating environments where people feel safe expressing disagreement, where dissent is welcomed rather than punished. And organizations that suffer repeated Abilene paradoxes often have cultures of false harmony, have norms that discourage challenging proposals, have leaders who interpret dissent as disloyalty, and these cultures create conditions for Abilene, create pressure toward agreement, and preventing the paradox requires changing culture, requires valuing truth over harmony, requires encouraging people to voice concerns. And this is difficult, requires conscious effort, requires leadership that models disagreement, that rewards dissent, that avoids shooting messengers. Another lesson is about decision-making procedures, about how groups can avoid Abilene through structured processes, through anonymous voting, through devil's advocate roles, through explicit checking for consensus, through asking not just who agrees, but who disagrees and why. And these procedures create space for dissent, create permission to voice opposition, and reduce pressure toward false consensus. And effective groups use these procedures systematically, build them into decision-making, recognize that surface agreement may hide opposition, and these procedures are especially important for high-stakes decisions, for commitments that are costly to reverse. And the trip to Abilene is costly, is unpleasant for everyone, and could have been avoided with better communication. The Abilene paradox also appears in organizational settings, in corporations where teams pursue strategies that no one really supports, in committees that adopt policies no member wants, in groups that invest in projects everyone privately doubts. And these organizational Abilenes are costly, waste resources, damage morale, produce outcomes that serve no one's interests. And preventing them requires organizational awareness, requires training people to recognize Abilene dynamics, requires creating cultures where speaking up is safe, where dissent is valued, and many organizations fail at this. Have cultures of deference, have hierarchies, where subordinates agree with superiors even when privately opposed. And these cultures are Abilene-prone, create repeated paradoxes, and organizational effectiveness requires breaking these patterns. Some argue that the Abilene paradox is overstated, that genuine cases are rare, that most group decisions reflect genuine preferences of at least some members, and while everyone agreeing despite everyone opposing is uncommon, partial Abilene is more common, where some members oppose but remain silent, and the group pursues a course that a vocal minority supports while a silent majority opposes. And this partial Abilene is still problematic, still produces suboptimal outcomes, and preventing it still requires encouraging dissent, requires creating safety for opposition. The paradox also raises questions about responsibility, about who is responsible when groups make decisions no one wants. And the answer is everyone and no one. Everyone contributed through silence, through false agreement, through failure to voice opposition, but no one individually caused the outcome. No one individually chose wrongly. Each made a reasonable social decision to accommodate perceived group preferences, and the collective outcome is worse than any individual action merited. And this shows how social dynamics can produce results that exceed individual culpability, can create group failures that no individual intended. And avoiding such failures requires collective awareness, requires group-level solutions, requires changing communication patterns and decision procedures. The family sits on the porch afterward, hot and tired and annoyed, and someone admits they didn't want to go, and the admissions cascade. And everyone realizes the absurdity, realizes they collectively did something no one wanted, and the Abilene paradox is revealed, and laughter mixes with frustration, and the lesson is learned. The importance of honest communication, the danger of false consensus, the need to voice dissent, and the paradox remains a permanent reminder that groups can fail not just through conflict, but through excessive agreeableness, through mistaken assumptions about others' preferences, through social pressures that suppress authentic communication, and the Abilene paradox endures as a cautionary tale about group decision-making, a demonstration that agreement is not always consensus, that unanimous decisions can be wrong, and that preventing collective irrationality requires creating environments where dissent is safe, where truth is valued over harmony, and where groups communicate authentically rather than accommodating falsely. Schrödinger's cat, the pet that's both alive and dead. A cat sits in a sealed box, a box that cannot be opened or observed from the outside. And inside the box with the cat is a device, a quantum mechanism that has a 50% chance of killing the cat within 1 hour and a 50% chance of leaving the cat alive. Perhaps a vial of poison that will break if a single radioactive atom decays. And the decay is a quantum event, genuinely random, with no way to predict whether it will happen in the next hour. And so after 1 hour has passed, the cat is either alive or dead. 50-50 odds. And this seems straightforward, but the paradox emerges when quantum mechanics is taken seriously, when the rules of quantum theory are applied consistently, because quantum mechanics says that before a measurement is made, before the box is opened and the cat is observed, the system exists in a superposition, a combination of both possible states simultaneously. And so the cat is both alive and dead at the same time, existing in a strange limbo where neither state is definite until observation collapses. The superposition and forces the system into one state or the other. And this is Schrödinger's cat, a thought experiment devised by physicist Erwin Schrödinger in 1935 to illustrate what he saw as the absurdity of applying quantum mechanics to macroscopic objects to show that something was wrong with the standard interpretation of quantum theory. Imagine the situation step by step. At the beginning, the cat is alive, the radioactive atom has not yet decayed, and the quantum state is well defined. But as time passes, the atom enters a superposition of decayed and not decayed, because quantum mechanics describes it with a wave function that assigns amplitudes to both possibilities, and these amplitudes evolve smoothly, and the atom is in a state of quantum indeterminacy, neither definitely decayed nor definitely not decayed until a measurement is made. And this indeterminacy is not ignorance, not a matter of the atom being in one state or the other, and we just do not know which, but a genuine feature of quantum reality. The atom literally does not have a definite state until measured, and because the poison release is coupled to the atom's state, the poison is both released and not released, and the cat is both dead and alive, existing in a superposition of macroscopic states. And this conclusion seems absurd, seems to violate everything we know about cats and boxes and life and death, and Schrödinger intended it to be absurd, to show that something must be wrong with the orthodox interpretation of quantum mechanics, that the theory cannot be applied consistently to large objects, that there must be a boundary somewhere between the quantum realm, where superpositions occur, and the classical realm, where objects have definite states. The paradox has generated an enormous amount of discussion and debate in physics and philosophy, with different interpretations of quantum mechanics offering different resolutions. The Copenhagen interpretation, the dominant view in Schrödinger's time, says that the wave function collapses upon measurement, that the act of observation forces the system into one definite state. And so when the box is opened and the cat is observed, the superposition collapses and the cat becomes definitely alive or definitely dead. But this raises questions about what counts as a measurement, about what constitutes an observer, about whether consciousness is required to collapse the wave function, or whether any physical interaction suffices. And these questions remain controversial, and the Copenhagen interpretation does not provide clear answers, does not specify where the quantum classical boundary lies. The many worlds interpretation offers a different resolution, saying that the wave function never collapses, that both outcomes occur, that the universe splits into two branches, one where the cat is alive and one where the cat is dead, and both branches are equally real. And the observer also splits, becoming two versions, one observing a live cat and one observing a dead cat. And each version believes they have observed a definite outcome. But from a global perspective, both outcomes happen. And the superposition is resolved not by collapse but by branching. And this interpretation avoids the measurement problem, avoids the need to specify what counts as a measurement. But it introduces other difficulties: the proliferation of parallel worlds, the question of what it means for both outcomes to be real, and whether this is a genuine solution or merely a reformulation of the problem. Decoherence theory provides another perspective, focusing on the interaction between the quantum system and its environment, and it shows that macroscopic objects, like cats, are constantly interacting with their surroundings, with air molecules, with photons, with thermal radiation, and these interactions cause the quantum coherence, the delicate phase relationships that allow superpositions to be destroyed very rapidly in a fraction of a second for macroscopic objects. And once coherence is lost, the system behaves classically, appears to be in one definite state, and so the cat never actually exists in a superposition of alive and dead, or exists in such a state for only an immeasurably short time before decoherence converts it to a classical mixture, a probabilistic state where the cat is either alive or dead. We just do not know which until we look. And this dissolves the paradox by denying that macroscopic superpositions persist long enough to be observable. The paradox also raises questions about the role of consciousness in quantum mechanics, about whether an observer must be conscious to collapse the wave function, and some interpretations suggest that consciousness plays a special role, that the cat remains in superposition until a conscious being opens the box and perceives the outcome. And this view has been criticized as mystical, as importing mind into physics in ways that are unnecessary and unhelpful. And most physicists reject it, preferring interpretations that treat measurement as a physical process involving interactions with macroscopic devices not requiring consciousness. But the question remains open, debated, unresolved, and Schrödinger's cat sits at the center of this debate, a symbol of the deep puzzles that quantum mechanics presents. Visualize the box, sealed and opaque, and inside the cat waits, and the quantum device ticks, and the atom hovers in superposition. And according to quantum mechanics, the entire contents of the box, the atom, the device, the poison, the cat, all exist in a superposition of two macroscopically distinct states: alive cat no decay and dead cat decay. And this superposition is described by a wave function that smoothly evolves, and the two branches of the wave function correspond to two different realities. And yet before the box is opened, there is only one box, one cat, one system. And the paradox is that quantum mechanics seems to say the cat is both alive and dead. While common sense says the cat is either alive or dead, we just do not know which. And this clash between quantum formalism and classical intuition is the heart of Schrödinger's cat, a paradox that has no agreed upon solution. that different interpretations resolve in different ways, and that continues to drive research in the foundations of quantum mechanics. In efforts to understand what measurement means, what quantum states represent, and how the quantum world relates to the classical world we experience, the box sits on the table, the hour passes, and the cat's fate is sealed. Or is it? Or is the cat in limbo, suspended between life and death, waiting for observation to make reality definite? And the paradox endures, not because physicists do not understand quantum mechanics, but because quantum mechanics, understood correctly, leads to conclusions that seem impossible, that violate everyday experience, that force choices between interpretations that are empirically equivalent but conceptually divergent. And Schrödinger's cat remains the most famous illustration of this strangeness, a thought experiment that has entered popular culture, a paradox that symbolizes the weirdness of quantum reality. And the cat, alive and dead, real and hypothetical, continues to haunt physics and philosophy, a permanent reminder that the quantum world is not merely different in degree from the classical world, but different in kind, governed by rules that defy visualization and resist intuitive understanding. And the paradox persists, unresolved in the deepest sense, a puzzle that reveals the limits of human intuition and the challenge of making sense of a theory that works perfectly in practice but remains mysterious in principle. Skolem's paradox. Set theory describes infinite sets of different sizes, and Georg Cantor proved that the real numbers are uncountably infinite, that they cannot be placed in one-to-one correspondence with the natural numbers, that there are more real numbers than natural numbers. And this is one of the foundational results of modern mathematics, a theorem that establishes a hierarchy of infinities. But Thoralf Skolem discovered a paradox, or what appears to be a paradox, that threatens this result. And the paradox is that any consistent first-order theory that has an infinite model also has a countable model, a model where the domain consists of only countably many elements. And this is the Löwenheim-Skolem theorem, and applying it to set theory yields a troubling conclusion. If set theory is consistent, then it has a countable model, a model where the universe of sets is countably infinite. And yet within this model, the axioms of set theory are satisfied, including Cantor's theorem, which proves that the real numbers are uncountable. And so we have a countable model of set theory in which there exists an uncountable set. And this seems contradictory. How can a set be uncountable if the entire universe is countable? How can there be more real numbers than natural numbers if the whole model has only countably many elements? And this is Skolem's paradox. The resolution lies in understanding the distinction between internal and external perspectives, between how things appear from inside the model and how they appear from outside. From inside the countable model of set theory, all the axioms hold. Cantor's theorem is provable. The real numbers have no enumeration within the model. No bijection between the reals and the naturals exists as far as the model is concerned. And so internally, the reals are uncountable. But from outside the model, from the perspective of someone who can see the entire structure, the model itself has only countably many elements, and there exists a bijection between the elements of the model and the natural numbers. A bijection that is not itself an element of the model, that does not correspond to any set or function within the model. And so externally, the model is countable. And this distinction between internal and external is the key to resolving the paradox. Uncountability is relative. It depends on what bijections are available, and different models have different bijections. Skolem's paradox reveals something profound about the nature of mathematical existence and the limits of first-order logic. It shows that first-order logic cannot pin down the cardinality of infinite sets, that the concept of uncountability is not absolute but relative to a model, that what counts as uncountable in one model may be countable in another, and this relativity is a consequence of the expressive limitations of first-order logic, which can only quantify over-elements of the domain. not over arbitrary functions or sets of elements. And so first-order set theory cannot express the existence of a bijection between two sets in an absolute way, cannot say, in a model-independent manner, that a set is countable or uncountable. Some philosophers and logicians find this relativity troubling, a sign that first-order set theory is inadequate as a foundation for mathematics, that a stronger logic, perhaps second-order logic, which allows quantification over sets and functions, is needed to capture the intended meaning of set theoretic concepts. And in second-order logic, the Löwenheim-Skolem theorem does not hold. There are categorical characterizations of structures, including characterizations of the natural numbers and the real numbers that pin down their cardinality uniquely, and so second-order logic avoids Skolem's paradox by being more expressive, by allowing statements that distinguish countable from uncountable models. But second-order logic has its own difficulties. It lacks complete proof systems. There is no algorithmic procedure that can, in principle, prove all second-order truths, and so the gain in expressiveness comes at the cost of losing some of the nice logical properties that first-order logic enjoys. Others embrace the relativity revealed by Skolem's paradox, arguing that it shows the conventional or perspectival nature of mathematical concepts, that cardinality is not an intrinsic property of sets but a relation between sets and models, that what we call uncountable is simply a set that lacks an enumeration within a particular model, and that different models can disagree about what is countable without any of them being wrong. And this perspective aligns with a pluralistic or model-theoretic approach to mathematics, where there is no single intended model of set theory, but many models, each with its own internal structure, and what is true varies from model to model, and mathematical truth is relative to a choice of model. Skolem's paradox also connects to issues about the definiteness of the continuum, about whether the set of real numbers has a well-defined cardinality, and the continuum hypothesis, which asks whether there is a set whose cardinality is strictly between that of the natural numbers and the real numbers. And this hypothesis is independent of the standard axioms of set theory, meaning that neither the hypothesis nor its negation can be proven from the axioms. And some mathematicians interpret this independence as evidence that the cardinality of the continuum is not a definite matter of fact, but depends on additional assumptions or on the choice of model. And Skolem's paradox reinforces this interpretation by showing that even the distinction between countable and uncountable is model-dependent. The paradox remains a touchstone in the philosophy of mathematics and the foundations of logic. It illustrates the limits of first-order logic, the relativity of model-theoretic notions, and the gap between formal systems and intended interpretations. And it forces careful thinking about what it means to say that a set is countable or uncountable, about whether mathematical concepts have absolute meanings or are always relative to a framework, and about the relationship between syntactic provability and semantic truth. And the paradox has no simple resolution. Different philosophers and mathematicians draw different lessons, some seeing it as a defect of first-order logic, others as a feature revealing deep truths about the nature of infinity and cardinality. And the debate continues, with implications for how we understand the foundations of mathematics, the status of set theory, and the nature of mathematical truth. The countable model sits in logical space, containing sets and functions and real numbers, and within this model, Cantor's theorem holds. The reals are uncountable, no enumeration exists, but from outside the model, the whole structure is countable, all its elements can be listed, and the real numbers of the model, uncountable internally, are countable externally. And this doubling of perspective, this split between internal and external, is the heart of Skolem's paradox, a demonstration that perspective matters, that truth is not always absolute, that models can disagree, and that first-order logic, powerful as it is, cannot capture all the nuances of infinite cardinality, and the paradox endures, a puzzle that has shaped logic and set theory, a challenge that continues to generate discussion and debate, and a reminder that even the most basic mathematical concepts, even the notion of how many, become subtle and contested when applied to infinite collections. The barber paradox. In a small village, there lives a barber who follows a single rule. He shaves all and only those men in the village who do not shave themselves. And this rule seems simple enough until the question emerges: does the barber shave himself? And suddenly the logic collapses into contradiction. If the barber shaves himself, then he belongs to the group of men who shave themselves, which means according to the rule, he should not shave himself because he only shaves men who do not shave themselves. But if he does not shave himself, then he belongs to the group of men who do not shave themselves, which means according to the rule, he must shave himself because he shaves all men who do not shave themselves, and the loop tightens without escape, spinning endlessly between two impossible options. Bertrand Russell popularized this version of his own paradox as a way to make the abstract problem of self-referential sets more accessible, more human, more vivid, because a barber is easier to imagine than a set of all sets that do not contain themselves. Yet the logical structure remains identical, a rule that turns inward and devours its own coherence. The paradox reveals something unsettling about definitions and categories, that not all rules can be consistently applied, that language and logic can conspire to create situations that seem perfectly reasonable until examined closely, and then they shatter. Some philosophers argue that the barber simply cannot exist, that the rule itself is contradictory, and therefore no such barber could ever follow it in reality, while others suggest that the problem lies in assuming the rule must apply universally, that perhaps the barber is exempt from his own rule, or that the village contains no barber at all. The paradox also exposes the danger of self-reference, the way that statements or rules that loop back on themselves can generate infinite regress or outright contradiction. And this has implications far beyond barbershops, touching mathematics, computer science, law, and any system that attempts to regulate itself from within. In set theory, the barber paradox mirrors Russell's discovery that naive set theory permits the construction of sets that cannot exist without contradiction, forcing mathematicians to impose restrictions on which sets are allowed to form, creating hierarchies and boundaries to prevent self-reference from poisoning the system. The barber stands at the edge of reason, a figure trapped in a loop of his own making, unable to shave or not shave without violating the very rule that defines his existence, and in this way, he becomes a symbol of the limits of logic, a reminder that not every question has an answer, that some problems resist resolution no matter how carefully they are examined. The paradox lingers in the mind, a simple story about a man and a razor that somehow reveals a crack in the foundation of thought itself, and once noticed, it cannot be ignored, appearing again and again wherever rules turn inward, wherever systems attempt to contain themselves, wherever language reaches the boundary of what it can coherently express. The bootstrap paradox. There exists a strange loop in time where cause and effect chase each other in a circle, where information or objects appear from nowhere, with no origin, no creator, no beginning, and this is the bootstrap paradox, named after the impossible act of pulling oneself up by one's own bootstraps, a paradox that emerges whenever time travel creates a causal loop that has no starting point. Imagine a time traveler who loves a particular symphony, and one day they decide to travel back in time to meet the composer, but when they arrive in the past, they discover that the composer has not yet written the symphony, and so the time traveler, eager to hear the music again, writes down the notes from memory and gives them to the composer, who then publishes it as their own work, and the symphony becomes famous, and years later the time traveler hears it and falls in love with it and decides to travel back in time to meet the composer, and the loop is complete. The question that haunts this scenario is simple and unanswerable. Who actually composed the symphony? The composer received it from the time traveler, and the time traveler received it from the composer, and neither of them created it. The information simply exists within the loop, passed from future to past and back again, with no point of origin, no moment of creation, no author. The bootstrap paradox differs from the grandfather paradox because it does not involve contradiction. The timeline is perfectly self-consistent. Every event follows logically from every other event. There is no clash between cause and effect, and yet something feels deeply wrong, an intuition that things must come from somewhere. That information cannot simply exist without being created. The paradox appears in many variations: a book that writes itself, a watch that is given to a younger version of oneself, who then keeps it for decades before giving it back, a technology that is brought from the future and used to invent itself, and in each case the object or information becomes eternal, trapped in a loop of time, aging perhaps, but never truly beginning or ending. Some physicists accept the bootstrap paradox as a genuine possibility if time travel is real, arguing that closed time-like curves, paths through space-time that loop back on themselves, are permitted by general relativity under certain conditions, and that such loops might allow for causally self-sufficient systems where the past and future are mutually dependent. Others find the paradox deeply troubling, a sign that something is wrong with our understanding of causation, entropy, or time itself, because information in a loop would violate the second law of thermodynamics, which states that entropy always increases, that order does not arise spontaneously from disorder, and yet in a bootstrap loop, the information appears to be perfectly preserved, never degrading, never increasing in entropy, existing in a kind of timeless stasis. The many worlds interpretation offers one way out, suggesting that the time traveler who delivers the symphony creates a new branch of reality, and that in their original timeline, the symphony had a different origin, but this solution feels like cheating, multiplying universes to avoid the discomfort of the loop. The bootstrap paradox forces confrontation with deep questions about the nature of causation, whether causes must always precede effects, whether the universe permits closed causal loops, and whether existence itself requires an ultimate origin, or whether some things can simply be eternal and self-caused, through time without beginning or end, defying the intuition that everything must come from something, that there must always be a first cause, a prime mover, a starting point from which all else flows. The binding problem: how your brain unites what it processes separately. A neuroscientist examines how the brain processes visual information, discovers that different features of objects are processed in different brain regions. Color is processed in one area, motion in another, shape in a third, orientation in a fourth, and all these features are analyzed separately, by specialized modules, by distinct populations of neurons. And yet when you look at a red ball moving to the right, you do not experience color, motion, and shape as separate. Do not see redness here and roundness there and rightward motion elsewhere, but see a unified object, a red round ball moving right, and all the features are bound together, are experienced as properties of a single thing. And this creates the binding problem, the puzzle of how the brain, which processes features separately, creates unified conscious experiences, how separate neural processes give rise to integrated perception, how the many become one. And this problem is fundamental, touches on the nature of consciousness, on how neural activity becomes experience, on what unifies experience into coherent wholes, and no complete solution exists. Various theories have been proposed, but the binding problem remains one of the deep mysteries of neuroscience, a gap between our understanding of neural processing and our understanding of consciousness. Imagine the visual system as a factory, with different departments processing different aspects of the product. One department handles color, another handles shape, another handles location, and all work in parallel, all process simultaneously, and each department produces its output color information, shape information, location information, and somehow these separate outputs must be combined, must be integrated into a unified representation, must be bound together so that you experience a red ball rather than redness and roundness as separate unlocalized features. And the binding problem asks how this combination occurs. What mechanism ensures that the right features are bound together, that the redness is attributed to the round object and not to the square object that happens to be present in the scene. And this correct attribution, this accurate binding, is critical for coherent perception, for navigating the world successfully, and yet how the brain achieves it remains unclear. The binding problem has two aspects: the feature binding problem, which asks how different features of the same object are bound together, and the object binding problem, which asks how different objects are kept separate, are not confused with each other, and both aspects are challenging. Both reveal that perceptual unity is not given automatically by neural processing, but requires some mechanism, some process that groups features appropriately, and various mechanisms have been proposed. Attention has been suggested as a solution. The idea that attention binds features, that attended objects have their features integrated, while unattended objects do not. And this explains why feature binding errors occur when attention is diverted, why illusory conjunctions occur where features from different objects are misbound, are attributed incorrectly. Visualize attention as a spotlight that illuminates objects one at a time, and within the spotlight features are bound, are integrated, and outside the spotlight features remain separate, are not integrated, and this attentional binding theory has some support, has experimental evidence showing that feature binding requires attention, that without attention, features can be perceived separately without being bound correctly, and illusory conjunctions are more common under conditions of inattention, supporting the idea that attention is necessary for binding. But attention cannot be the complete solution, because some binding occurs pre-attentively. Some feature integration happens automatically before attention is applied, and so attention is part of the story, but not the whole story. Another proposed mechanism is temporal synchrony, the idea that neurons representing features of the same object fire in synchrony, fire together, and this synchrony is the binding code, is what marks features as belonging together and neurons representing different objects, fire at different times or with different phases, and this temporal separation keeps objects distinct, prevents their features from being bound together. And this synchrony theory has been influential, has generated extensive research, has led to discovery of synchronized neural oscillations in visual cortex, but the theory faces challenges. It is not clear that synchrony is sufficient for binding, it is not clear that consciousness depends on synchrony, and some experiments have failed to find the predicted correlations between synchrony and perceptual binding, and the theory remains controversial. A third approach argues that binding occurs through convergence, through hierarchical processing, where features are combined in higher-level areas, and early visual areas process features separately, but project to higher areas that represent combinations, that have neurons responding to specific conjunctions of features. And these conjunction neurons represent bound objects, represent integrated wholes, and binding is achieved through this hierarchical architecture, through neurons that explicitly encode feature combinations. And this approach has support from single neuron recordings showing that higher visual areas have neurons with complex selectivity, neurons that respond to specific combinations of shape and color and motion, and these neurons could be the neural basis of bound object representations. The binding problem also connects to consciousness, because unified conscious experience seems to require binding, seems to require that separate neural processes be integrated into coherent wholes, and some theories of consciousness, like integrated information theory, make integration central, argue that consciousness arises from integrated information, from systems where different parts interact and constrain each other, and binding as a form of integration is the combination of separately processed features into unified representations. And understanding binding may be crucial for understanding consciousness, may reveal how neural processes give rise to unified experience. The problem also has practical implications for understanding neurological conditions where binding fails, where patients see features but cannot bind them correctly, and such conditions exist. Balint syndrome is one example, where patients can see individual features but cannot perceive objects, cannot integrate features into wholes. And these patients provide evidence that binding is a genuine process, is not automatic, can be disrupted by brain damage. And studying these patients helps understand normal binding, helps identify the brain regions and processes necessary for feature integration. Some philosophers argue that the binding problem is really a problem about consciousness, about how physical processes give rise to subjective experience, about the hard problem, and binding is one aspect of this, is the problem of how separate neural processes give rise to unified conscious experiences. And solving the binding problem may require solving the hard problem, may require understanding how neural activity becomes experience. And this makes binding one of the deepest problems in neuroscience, a problem at the interface between neuroscience and philosophy of mind. The brain processes features separately, color here, motion there, shape elsewhere, and yet you see unified objects, see red round balls moving, see integrated wholes, and how this integration occurs, how the separate processes give rise to unified experiences, remains one of the great unsolved problems. The binding problem stands, challenging, fundamental, revealing a gap between our understanding of neural processing and our understanding of perception. And various theories exist, various mechanisms have been proposed. Attention, synchrony, convergence, but no theory is complete. No theory explains all aspects of binding, and the problem persists as one of neuroscience's deepest mysteries. A puzzle about how unity emerges from multiplicity, how the brain binds what it processes separately, and the question remains open. The mechanism remains elusive, and the binding problem endures.